This video is the first one that deals with Chapter 10. Now we move into radical expressions, rational expressions, and we get a basic introduction in this section about what is a radical. Some of them you've seen before, maybe some of the graphs and things are a little bit new, and then in future videos we'll move into rational expressions, which are things that are divided. So it's worth taking a few minutes to go over. We'll start with the definition of what a square root is, and the definition is that last bullet point on here. The number b is a square root if b squared is equal to a. So 3 is a square root of 9 because I can take 3 squared and it'll give me back 9. There's notation that goes along with these square roots, and I'm sure you've seen at least some of these before. Every positive number has 2 square roots, a positive one and a negative one. So if you were to solve an equation like x squared equals 36, you would take the square root of both sides and you would tell me that x equals plus minus the square root of 36, which is plus minus 6. Why? Because 6 squared will give me back 36, but also negative 6 squared will give me back 36. But yet when the question just says find the square root of 36, we don't give both roots because what we're asked to find is really the principal square root. All right, so I've given you a positive number, give me the square root of 36. You wouldn't answer and say the answer is negative. You would say the square root of 36 is 6. And so that's the difference. If it's some number squared equals 36, then yes, there's 2 possible numbers that will give me 36. But if the question simply says, give me the value of the square root of 36, we assume it's just the positive or the principal square root, and we only give the 6 without the plus minus. That little check mark symbol on top we call radical sign. You'll see those when we also do cube roots as well. And there are names for all of these things. So if I have the square root of 36, that 36 is called the radicand, and the expression containing the radical sign is called a radical expression. So this whole thing is a radical expression. Now, I mean, it could be something more complicated. It could be the square root of 2x plus 4, right? That's a radical expression as well. And the expression under it is that whole 2x plus 4, and that's called the radicand. We don't use that language a lot, but if you happen to see it, that really is the correct expression for that. All right, so some examples of radical expressions are sitting down the bottom. The square root of 7. 7 is not a perfect square, but the square root of 7 is a perfectly legitimate radical expression, and it has a numerical value. It's irrational, but it's still a numerical value. 6 plus the square root of x plus 2 is another radical expression, and that third one is a fraction underneath the radical, which again is still a radical expression. The radicand would be that 5x over 3x minus 4. All right, so evaluate each square root. Oh, look, I already did the first one. The square root of 36 is 6. That second one, the square root of 0.64. Well, if I asked you for just the plain old square root of 64, the question would be what number times itself gives me 64? And of course, the answer is 8. But this thing here is really asking for the square root of 64 hundredths, right? 0.64 is 64 hundredths. Well, the way I take a square root there is by taking the square root of the numerator, square root of the denominator. I can break them apart like so. Square root of 64 is 8. Square root of 100 is 10, because 10 times 10 gives me back 100. So I get an 8 over 10, which means I can write my answer in 2 different ways. I could write it as 0.8, right? That's 8 tenths. Or I could simplify it and I could get 4/5. That's also the square root of 0.64. All right, the one down the bottom is solved similarly. The square root of 16 is 4. The square root of 25 is 5. All right, we saw some cube roots earlier in the course when we were dealing with those factoring questions, sums and differences of cubes, and I had kind of thrown some language in there about finding the cube root of things like x to the third and 8. Well, a cube root just means what number can I multiply 3 times to get that number back. So just like there's a list of perfect squares, there are lists of perfect cubes, right? Obviously, 1 cubed is 1. 2 cubed is 8, so 8 is a perfect cube. 3 cubed is 27, so 27 is a perfect cube. These things get big pretty quickly because you're multiplying them by themselves 3 times. The bigger the number, the faster they get up there. So 4 to the third is 64. 5 to the third is 125, and those are probably the ones that you'll see most often. Maybe a 6 or a 7 from time to time. 6 to the third is 216, and 7 to the third is 343. Much beyond that, you'll grab a calculator. Your cube root button on your calculator is going to be in a different place depending what kind of calculator you have. The one that I have has the cube root button above the 0 key. So you have to hit shift and 0, and that gives you the cube root. So like, try it out. Put a 64 in. And so if I type in a 64, and then I hit second, which is that yellow key that I have on the top. I have a TI-30. Second and the number 0, and then enter, it should give me a 4. All right, so that's the cube root of 64, gives me 4. On your calculator, it might be in a different spot, but they're generally keys above the standard numerical keys that you have on the calculator. All right, the number is a cube root if I can cube the number and get back the original one. So I can take the cube root of 64, and it'll give me 4. Why? Because 4 times 4 times 4 is 64. When you draw these radicals, make sure that 3 is enough inside that little check mark to make sure that it doesn't look like 3 times the square root of 64, because the answer to that is 24, right? 3 times 8 is 24. But that's not what the question is asking. It's asking for the cube root of 64. So just make sure when you write things out that whoever is interpreting your work can figure out what it means. Now, the one underneath that looks a little different. We're not used to seeing negative signs under radicals. Is that okay? Well, for a square root, the answer is no. For a cube root, yes, you can take the cube root of a negative number and it will give you an actual answer. Why? Because what number times itself 3 times gives you negative 25? Well, it's got to be a negative number. So how about negative 5? Try negative 5 times negative 5. That gives me positive 25. Positive 25 times negative 5 gives me negative 125. So sure enough, I can write the cube root of negative 125 is negative 5. The one down the bottom is evaluated in the same manner as a square root would. You can make it the cube root of 1 over the cube root of 8, right? You're allowed to break apart a cube root like that. Cube root of 1 is 1. Cube root of 8 is 2. So the cube root of 1/8 is 1/2. I took this from the textbook. I think it's just worth taking a look at because there are roots that go higher than cube roots, right? We have square roots, cube roots. I mean, you can take 27th roots of something. It all works out in a similar way. And that is, we call that little root over here the index. So if I gave you the cube root of something, right, the cube root of x, that 3 would be the index. It would tell me I'm taking the cube root. If the number underneath that cube root is positive and you're taking a root, then the answer is positive. That's the easy one. So it doesn't matter whether you're taking the cube root of 64 or the square root of 64. Cube root of 64 is 4. Square root of 64 is 8. You're taking roots of positive numbers. The answer is a positive number. The difference happens when that number under the radical is negative. So if I said take the cube root of negative 64, then this index over here is odd. That's what they're referring to. N is odd. So that index is odd. Then my answer is a negative number. The cube root of negative 64 is negative 4 because I'm multiplying 3 times, so I can do a negative times a negative times a negative and get a negative. It's as if n is even and the number underneath is negative, then my answer is not a real number. So I'm taking the square root. That means the index is 2. We don't generally write the 2 there, but the index is 2. The square root of negative 64 is not real. Now, I mean, it does have a designation. It's called a complex number, and we'll get to those at the end of this chapter, I think. It's really the beginning of my next unit, but we will get there. But it's not real. There's no number you can multiply by itself to get a negative, right? 2 negatives make a positive, 2 positives make a positive, so it's not a real number. All right, so this one says find each root if possible. Now, a fourth root means what number can I multiply by itself 4 times to get 256? Well, taking the fourth root is the same thing as taking the square root twice. So I happen to know that the square root of 256 is 16, and the square root of 16 is 4. So I'm going to go with 4. Now, how do I check my answer? I take my calculator, and I type in 4 to the 4th. So you're going to need that little caret key. The caret key is the one that looks like that. So if I type in 4 to the 4th, it'll give me back 256. All right, the fifth root of negative 243. So what number can I multiply by itself 5 times to get 243? You might think it's going to take a long time to get there, but these numbers get big very quickly. So first of all, this is odd. That's negative, so I know my answer is going to be negative. Right, what number times itself 5 times gives me 243? If I'm not sure, I'll try it. Right, try typing in my calculator 2 to the 5th. I can tell you 2 to the 5th is 32. How about 3 to the 5th? So I take my calculator, I type in 3, hit the caret key in 5, and oh look, I got 243. So even though the number is big, it doesn't take long to get there. So the the fifth root of negative 243 is 3. Now look at part C. It wants the fourth root of a negative number. So here, that's even. And I don't even have to think too hard. I can't take the fourth root of a negative number. There's no number that I can multiply by itself 4 times. That'll give me the negative, right? Four positive signs give me a positive. 4 negatives give me a negative. So this is not real. So you notice the directions said, find each root if possible. Well, that one's not possible. Now, here's something kind of interesting. This says, for every real number x, the square root of x squared is the same as the absolute value of x. If you're not convinced, give it a try. Put a couple of numbers in here. So suppose I use 4. What is the square root of 4 squared? Well, the square root of 4 squared, we do the square part first. Then we take the square root and we get 4. Right, so here I'm starting with x equals 4. Is that the same thing as the absolute value of 4? Sure it is. So for positive numbers, it's fairly obvious. What if I used x equals negative 3? What is the square root of negative 3 squared? Well, the first thing I would do is square negative 3. So negative 3 times negative 3 is 9. Square root of 9 is 3. So I put in a negative 3. I got out a positive 3. Isn't that what happens with absolute values? I put in a negative 3, and I get out a positive 3. If you're still not so convinced that this works, try graphing them. All right? So let me grab Desmos over here for just a second, and I'm going to put in 2 equations. I'll put in y equals the absolute value of x, and then I'll put y equals the square root of x squared. All right, I think it wanted. There we go. Okay, so now you notice I got the same graph. They're sitting right on top of each other. That's the square root of x squared. That's the absolute value of x. When I add the second one, it sits right on top of the first one. So the square root of x squared is the same thing as the absolute value of x. Whatever you put in, it returns back the positive answer. So if you put in a negative, it returns a positive. Put in a positive, it returns a positive. And clearly, put in a 0, and it returns 0. So what are we going to do with this newfound knowledge that we have here? Let's try to evaluate a couple of expressions. So it says, write each expression in terms of an absolute value. So let's do that and then see if there's anything we can do to simplify it. The first one, the square root of negative 5 squared. So the square root of something squared is the same thing as the absolute value. And so when we rewrite this, we get the absolute value of negative 5. Right? And then if we wanted to go one step further, yes, that actually evaluates to be 5. Over here, the square root of something squared is the absolute value. So the square root of x plus 3 squared becomes the absolute value of x plus 3. And that will help us when we go to solve equations, that we may not know what to do with the square root of something squared, but if you turn it into an absolute value, now it starts looking a lot like the stuff we did in the last unit. And then the third one doesn't work unless we factor it. Please don't break this apart into 3 parts. It doesn't work like that. This one, it turns out we can factor. How do we factor? We need 2 factors that multiply to be 9 that add up to be negative 6. Now, you could have used the perfect square trinomial pattern. I'm just thinking, what happens if you forgot what the perfect square trinomial pattern is? You still can factor this. You're looking for 2 factors that have the same sign, both negative, so I'm going to go with negative 3 and negative 3. Try foiling that out. I get a w squared. Minus 3w is minus 6w. Negative 3 times negative 3 is 9. So basically, I've turned this problem into the last problem with a minus sign and a different color ink. Okay. Square root of w minus 3 squared becomes the absolute value of w minus 3. The square root of something squared is the absolute value. All right, this wants me to evaluate. Okay, so I'm just taking functions and I'm putting in 1s and I'm putting in -2s. So what is f of 1? F of 1 is the square root of 5 times 1 plus 1. Well, 5 times 1 is 5 plus 1. So f of 1 is the square root of 6. I can't simplify it, so I just leave it like that. What is f of -2? F of -2 is the square root of 5 times -2 plus 1. So that gives me -10 plus 1, which is the square root of -9. Not real. The second one will work out just fine, because whatever I put in, I'm going to square it and add 4. So if I put in a 1, 1 squared is 1 plus 4 is 5, so I get the square root of 5. If I put in a -2, -2 squared is 4 plus 4, I get the square root of 8. All right, what do these things look like if I go to graph them? What does it look like when I go to graph the square root of x? Well, maybe it's helpful to make a table, so let's make a table of values. For this one, we better put some negatives in here and see if it works. This way we don't extend our graph beyond where it should be. So what if I put in something like a -2? Well, pretty quickly I can see that the square root of -2 doesn't exist. The same thing's going to happen with the square root of -1. What if I put in a 0? Square root of 0 is 0, that's good. Square root of 1 is 1. I'm going to pick a 4 and a 9 because look what I'm doing. I'm taking the square roots of numbers. So the square root of 2 and the square root of 3 are perfectly valid numbers. The square root of 2 is about 1.4. The square root of 3 is about 1.7. But they're awful hard to graph on that little grid that I have next door. So let's try to keep the numbers reasonable. So the square root of 4 is 2. Square root of 9 is 3. All right, let's change color and plot some points here. It starts at 0, 0. It goes through 1, 1. But if I stop there, it's going to look like a line, and it's not a line. So let's plot a couple of more points. 1, 2, 3, there's 4. So at 4, I get 2. 5, 6, 7, 8, here's 9. At 9, I get 3. It's a curve. Right, so in these curves, it comes up like that. If you know something about parabolas, that looks like half of a sideways parabola. And that's exactly what the square root of x is. It's half of a sideways parabola with nothing to the left of 0, 0. All right, so that's a basic simple one. Let's kick it up a notch over here. We're going to look at 2 more graphs in this section, and then we'll wrap it up. What if I put in values for the square root of 2x plus 6? So you might assume this is going to have a similar shape to the other one, but probably look a little bit different in terms of location on the graph. So I pre-chose some values for x that I know are going to work. So let's put in a -3. 2 times -3 plus 6. 2 times -3 is -6, plus 6 is 0. So if I put in a -3, I get out of 0. If I put in a -1, 2 times -1 is -2, plus 6. 6 minus 2 is 4. Square root of 4 is 2. What happens if I put in a 2? 2 times 2 is 4. 4 plus 6 is 10. So I get the square root of 10. Now, when I go to graph this, I'm going to graph something close to 3, right? Because the square root of 9 is 3. So that's going to be a little bit above 3. For 5, 2 times 5 is 10 plus 6 is 16. Square root of 16 is 4. And if I put a 9 in, 2 times 9 is 18. 18 plus 6 is 24. So yes, technically I get the square root of 24, but the square root of 24 is real close to 5. All right, let's plot some points. -3, 0. Here's -3, 0. -1, 2. +2 just above 3. 5 and 4. And then the last one will be 9 and just under 5. So here's what this graph looks like. It's still that curve, but you notice this starts in a different place and it has a little bit of a different shape to it. But still same basic idea, right? That 2x plus 6, as we'll eventually learn, pushes that whole thing 3 units to the left, because where is that 2x plus 6, 0? It's 0 and x is negative 3. That's why I started my list there. If I started it any further left than negative 3, I'd get negatives under the radical, and that wouldn't work. All right, one more. This one's a cube root function. All we've been doing are square root functions. What do cube root functions look like? So let's pick some nice values. Let's not pick 7s and 17s and 23s. So let's pick some values for x and the cube root of x. So let's pick negative 8, negative 2, negative 1, 0, 1, 2, 8. I'm picking perfect cubes. Cube root of negative 8 is negative 2, right? Negative 2 times negative 2 times negative 2 will give me back negative 8. The cube root of negative 2, I probably shouldn't have put in there because that's not a perfect cube. Cube root of negative 1 is negative 1. Cube root of 0 is 0. Cube root of 1 is 1. And the cube root of 8 is 2. Okay. I mean, the cube root of negative 2 exists, but let's not worry about that. That's graph here. So negative 8, negative 2 is over here. Negative 1 is all the way over here. It goes to the origin, goes through 1, 1, and goes through 8, 2. Yeah, that's a weird looking thing. Let's see what it looks like when I connect the dots. Right, it rides up like this, up, and around. And even though I'm drawing it kind of flat, it actually does continue to increase. Right, so it's probably partway in between here, and then it will continue actually going down from here. Slowly though, right? Because the next point that it hits on the right side won't be until x equals 27. That's when it'll make it up to 3. So that's way off this screen, probably somewhere off your computer screen into a wall somewhere. So it's going to take a while until it gets to 27.3. So it looks like it's flat. It's not completely flat, but it is moving very slowly. All right, that's the end of this section. Next video, we'll talk about rational exponents.